Hello, dobry dzien, namaste, estas, good afternoon, good morning, good evening, wherever you are around the world. Abadia. My name is Etietop Demas Abraham. You can call me Eti. Today we will be performing a task on logistic regression and k-nearest neighbors. You can check out my previous video about k-nearest neighbor. I will be solving a problem here, practical one. It's about some pulsar stars, and we will be identifying them using. We'll identify a new star to find out, the probability of it being a specific type of star. And we would do this with logistic regression. We'd also do this with k nearest neighbors. Logistic regression is like linear regression. However, it works for di dichotomous variables. I'm sure that's what it's called. Basically, variables that hold two values, true or false, 0, 1, yes or no. So we will be predicting new stars using logistic regression and k nearest neighbors and figure out the probability of these stars being in a specific class. So this is a kind of supervised classification machine learning model. Let's get started. All right, just gonna reduce this. Okay, and so this is the question we'll be solving today. Let's go one step at a time. So the data sets pulsar stars includes information about stars that have been obtained during a universe survey. It's some sort of high time resolution universe survey. In order to determine one of the neuron star types, that is pulsars, the number of observations is we have about 100 we have about 17,000 data sets observed stars, and about 1,639 of these observations are pulsars. We have 8 predictors. Predictors basically are the variables that you analyze to determine what target or what class this variable belongs to. So they predict the I'm tired of using the words predictors. The predictors are independent variables. They do their own things by themselves. But based on what they do, we want to determine if the resulting effect of their independency and activities is A or B, is 0 or 1, is yes or no in case of logistic regression. So in this case, we have about 8 continuous predictors, the average value of the integral profile, and we have the target column as our response. This is what we're trying to figure out or classify or predict targets of the stars. All right, so let's get to work. So the data set is available in PostgreSQL. Let's log into Oracle and get into the SQL part of life. All right. So let's see. The name of the table is pulsar stars, and we need to draw a sample from the observations. So let us do that. So the sample we're looking for is one where the target is 0 and the MIP is in the set between 82 and 84. Okay, let's do that first. So let's do a select statement. Select all from pulsar stars where target is equal to 0. And what else did they ask for? Was it MIP? Yep, where MIP are what RP was the value we're getting there? is between 82. I'm just gonna copy this. Is between 82 and 84. Let's see what the statement looks like. All right. So we have this our basic our data set, so we can download this. Our This is our first sample. I'm gonna run the downloads and quickly to the second one where where target is 1 and MIP is between 83 and 92. Okay. So we change this to 1 and we change the range to 83 and 92. We run that and we got the values. Let's download this. So these are basic work. We're getting the sample data sets. Let me put this together in Google Drive or Excel, Google Sheets, so that it's easier for us to visualize what the data looks like. So we're going to start by importing this report that we just got, which is a sample data set. Let's do 6. And this is in CSV format. So let's replace the current sheet. And let's do the same thing for create a new sheet for 7. Let's import this data set. Quite easy, right? 7. And we're going to replace the current sheet. And we want to combine this because it's one data set, right? So I'm going to create a new sheet and I will combine both data sets, copy, paste, and I'm going to copy and paste here as well for the second sheet, but I won't copy the header, of course. But you can already see these values are looking quite interesting. Okay, let's just analyze these values a bit. So there's the MIP variable. Let's name this data sheet data. This is 0, 0, target 0, and this is target 1, target 1, and this is sample target 0 and 1. Okay, so there's MIP 83, STDIP, EKIP. All these are our independent variable STDC, EKC, SC, and this is a target. These values look like they would need to be normalized. The variations is quite, you see EKIP is 0.5 while MIP is 83. The weight is different. So let's get to the next question. So now we have the sample data set. So 1 is good. Now we need to, of course, perform a linear normalization of all the predictors, and we're going to do this in Azure. I like to call it Azure anyways, but it says Azure. So let's get to Azure. Quickly get this doing. Let's get this going. So we're going to normalize all the predictors, and our predictors are basically MIP to SC, and this is our target. Let's download this CSV because we would need that. Data sets are in Azure. All right, Azure, here we are. So like in my previous videos, Azure is quite easy to use. It gives you basic understanding of how to play with studios. It's a good starting point. So let's upload our data set, data sample, target 0, target 1. That's correct. And we have that. Let's quickly go into our experiment and create a new experiment, a blank one. Clear this up. All right, so we want to first drag our data set, which we just uploaded. Uh, we call it target 0, target 1. And then we want to select, we want to select the fields. Basically, for that, we have to select columns in data set that we're interested in. Remember, our task right now is to basically normalize the data set. But first, let's do some selection of this data set. So I need to get all our variables into our selector from the CSV, and then we need to get the normalize data. So we are normalizing not everything, we're normalizing the predictors, and the targets is 0 or 1 needs no normalization. Okay, so to normalize, we had some instructions that I think the random seed just makes sure that the results are replicable. It's not a big deal, but let's follow instructions. It says, no, not random seed. Random seed is for a different task. It says we should use the mean max method for normalization. There are different types of normalization. There's the mean max, which is the easiest one. There's logistic, there's log normal. So we're doing mean max, and let's launch our columns. I like to use the names, like you already know. Let me run this so I can reselect the exact variables I need. In this case, our target variables. So I'm going to do that selection again. I like to reload this so that the pre-selection from this by name columns is selected, and I can push this one back. Right. Let's run that again. And as that is running, let's see what the question is. All right, after normalization, find the sample mean of the MIP variable. Okay, let's see. We got 0.2948 here. Let's view our transformed data set. And we are looking at the MIP, which is this column. And you can see the mean is 0.294. The median is 0.1363. And this is looking fine. Our data is all normalized. Now you can see the difference. Like previously, the variables had different weightages, like different weights. This is 83, MIP is 83, EKIP is 0.5. You need to normalize it so that you're able to perform our mathematical operations in the same weight. And that is what normalization is doing here for us. So everything looks good. Let's move to the next question. And in the next question, we need to train a logistic regression model with with the data sample that we got with a random seed of 2019. All right, this is easy. So logistic regression is quite easy to implement on Azure. Again, logistic regression predicts a variable or makes predictions for either true or false or yes and no. So how do we do that? Let's clear some space. Can I be smaller? No, I'm gonna be big. Let us do logistic. It's called two-class logistic regression, right? We want to train this model to understand our data set. So we're going to train this model. So the logistic regression, two-class logistic regression, and our normalized data would form the input to our training. We need to select our target variable, right? So the normalized data contains our predictors. This is our model, which will be trained on that data set. Uh, and the training would create a model for us that we would use to predict a new star to figure out what kind of star it is. That's the whole goal of this. That's the whole goal of this. So our model is trained. Let's see what's the question here. Uh, so after training, we need to classify a new star with the parameters. These are the predictions for the new stars, right? We don't know what the target is, so we need to figure out what the target is. And we would do that with our new model that we've created. This is our guy, train model, right? So how do we do that? So these new values, we can enter them manually. We don't have to create a new data set or new data sheet. And we can do manual data, is that what it's called? And data, it's called, let's look for it. Create data manually. I say that. All right, so we're gonna enter the data manually. So let's do, oh, no, that's not the data. Let's go copy the new star. That's the new star in the horizon. And we need to, we can, unselect this, but I like to make sure that I put a header so I know exactly what's going on. So let's copy this headers of our stars, which is basically the variable name. So MIP 0.337, STDIP, put some commas across them, EKIP, SIP, MC, STDC, EKC, and SC. We got our stars complete. Sweet. All right, so we have that. We have our trained model. Or maybe I want to, just to be sure, select the columns from this data. I like this to look clean. So let's connect that here, and let's launch column selector. I don't like this by rules. I don't like these rules. So let's run this so that I can use their select by names as usual. Okay. So, okay. Enter data manually. Did that run? Okay, let's just do MIP, for instance. Let's run. Okay, that's running. And now I want to properly select my data set. So launch, please name be enabled exactly. All right, so let's get all our data for our new star in. So our stars are in here. And now we need to test our star and score this model. So we use the score model to, figure out if our model is able to classify this new data set. Simple. I think we had there was requirements for. Let's go back to the question. Random seed as 2019 for our logistic regression model. We didn't do that, even though it's not that serious. Let's do it. 2019. Let's run the model. All right, it's looking good. Okay. So our model is currently working, trying to analyze this star. Like, who's this star? Is this star a 1? Is this star a 0? Let's see our results for this star. So our score data set, visualize. And the results are here. Our new star is categorized as a 1. Amazing. With a probability of 0.68, almost 0.7, that this star is a 1. And let's go to the question. So what is the probability of assigning the star to the pulsar class? And that's 0.68, so that's correct. Now we want to also try and classify this with our k-nearest neighbor. We've done logistic regression. K-nearest neighbor basically looks around your neighborhood and sees the other stars closest to you and figures out uh, within k number of neighbors, for example, which ones are the closest to you, and the closest neighbor to you would most probably uh, be the kind of star you are. And there's different mathematical ways of calculating the distances between stars or between objects. In this one, we're supposed to do the Euclidean distance. There's the Manhattan distance as well. There's the Manhattan. There's the other one, Euclidean Manhattan, and this one K. I keep forgetting the name. D infinity. D infinity is what I call it, but how's his name? I always forget. Anyways, let's get to that. So for this, we need to uh let's see k nearest neighbor. So let's take out the logistic regression models. We don't need that anymore. We don't need anymore. We don't need anymore. Thank you. You served us well. This is our new star. We don't need you. We don't need you. Our normalized data. Okay. Let's work with that. Let's use the metadata to kind of rename our variables, because when we're calculating distances, to unselect this, because when we're calculating distances, I don't want to be worried about the names. So I want x1, x2 mathematical conventions that are easier to understand. So let's launch the selector and get all our babies in there. Okay. And let's give them new names. So x1, x2, these are our predictors. x3, x4, x5, x6, x7. I think there are about 8 parameters, x8, and we will call our target y. Right? Makes our life easy, yeah? So this looks good. And then what I want to do now with k nearest neighbors, or you can watch the previous video. It's simple. We calculate their squared distance between points, and then we do a square root. For them, it's a very simple formula. So for that, we would use the SQL transformation component of our Azure SQL. We're gonna apply some transformations. I think we're good here. Okay, so let's get into SQL. So what we want to achieve here, we want to, let's first select x1, x2, x3, x4, x5, x6, x7, x8, and the y. Right, and then we want to also get the Euclidean distance, because this is the task. We want to find the distance between our new star and all the existing stars, and the closest stars to our star would most probably be would have a target of the closest stars. So the target of whatever the stars are would probably be the target variable for us, and that's how we're going to classify it. Okay, so let's do Euclidean distance. So that's the square root of, we're going to be performing the square roots for this new point. So let me copy them into the system. I'm just going to put them down here. Don't forget it. Okay, so the square root of our point, first point of x1, our star, minus x1, that's the distance between our star and The first parameter, we're gonna square that, and we're gonna do that for the rest of the variables. So quickly, power 0.5 minus the second variable, or we're gonna square this plus power third guy, that attribute minus the distance of x3. We're gonna square this plus power, we're at number 4, 1 2 3 4, and minus x4. You see why I changed the name? Because I'm not gonna go back and start doing APC and PDP, you know. Plus that plus power when 5, 1 2 3 4 5. So that is 0.721 minus x5 square plus power, where 6 is, wait, let's see, 1 2 3 4 5. 5 is 0.9, so this is 5, 0.9, and 6 is 0.72. Thank God I cut that. Minus x6 square plus, we're doing number 7 now. 7 is just a second to this guy, the last one. And minus x7 squared, and the final one is 0.261 variable, x8 minus x8 squared. Okay, we're gonna call this Euclidean distance, right? Okay, good. Let me delete this now. I remember, and we're doing as Euclidean distance from, by default, the table we're connecting to is called T1. Let's order by Euclidean distance, and ascending basically from low to high. So the smallest number is what we're interested in. I think that's the default, but that's all right. Okay, this looks fine. So let's run it. Usually you should have errors, and that's okay. And let's see. Our SQL is running, and yes, as expected, an error. So let's find that error quickly. Okay, so we selected x1, x2, x3, x4, x5, x7, x8, and y, and the square root of the power of this minus x1 plus power x2 power x3. There we go. What's this? Wait, x4 plus power x5. So I can quickly get the error, but let's read the error message anyways. 1 second. Request ID failed, square root component module status 400, missing database near syntax. There's a syntax error. Yes, I know there's a syntax error. Let's see. Select. Ooh. Select query x1, x8, y. Error. Okay, let's figure out this. Let's see what our data set here is looking like. Visualize. So we have x1, x2, x2, x4, x8, and y. That's correct. So let's look at this. Select x1, x2, x3, x4, x5, x6, x7, x8, y. Then also square root. Did I close the square second bar? Yes, I did. from T1. Wait, let's just order this. Select Q. Let me take this out. Let's run this first and see. Now we can start dissecting the error. I like to look at, let's look at this directly from here. Look at my square root power. Mm-hmm. 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 What's this? That's the error. Okay. No wala, no wala. I think we found it. I'm not sure where that copy paste came from. Well, we did prophesy that we would encounter errors. So now that we did, let's go fix it. So y, and we paste back our erroneous code and go back and find that error, which is this. So this is x5. X5 is the fifth variable. 1, 2, 3, 4, 5, 0.928. So x5, 0.928 minus x5. All right, let's run this baby. As Euclidean distance from, let's order again. Order by Euclidean distance ascending. All right, let's run this baby. We prophesy that we're not getting no more errors. Okay. Apply SQL transformation, loading, and we are good to go. So let's see our result set. And you can see that with k nearest neighbors, the closest, this is 1.0, the closest star to our star is this star. This first one, the one with a Euclidean distance of 1.0356. And you can see that the star is a 1, right? Which is similar to the prediction from our logistic regression. So let's see the answer. Wait. There's an error. Something is wrong. Again, this result is not correct. Did we calculate our Euclidean distance correctly? We need to go back to that. Okay, let's do that. So square root of, well, let's copy back our data set so that we are, I had to be, this is why I like to be really careful in this point. So square root of this minus x1. This 0.53 minus x2. 0.425 minus x3. 0.036 minus x4. 0.928 minus x5. 0.721 x6. 0.714 x7. That's a mistake. Not, yeah, these two numbers look the same and just keep, getting in the way of things. How do I have 0.72 everywhere? Jesus. Okay, so x7 is 0.714. X8 is 0.261. That mistake again is about to happen. It will not happen though. Okay, so let's double check. 0.2671472192836425. Okay, we're looking good. And let's run it one more time. We're about to get done with this. It's loading. Let's see. Transformation seems to be fast. Did that run? Let's run it again. It seemed too fast, too true, too true to be true. It's fast though. All right, let's see. Visualize. And there we go. The closest star to our star is still a one, like logistic regression, and the distance is 0.78, which is 0.78. And remember, previously, the probability of from the logistic regression gave us almost the same figure, 0.7, if you approximate. I mean, it's 0.8, but it's close enough. And that's logistic regression. Thank you for your attention. Have a beautiful, beautiful time. Goodbye.